Hello and thank you for joining us for this latest AMS webinar with ABB. My name is Nick Holt and I'm the editor of KUKA. My name is Nick Holt, I'm editor of Automotive Manufacturing Solutions. Today we've got Peter Klueger, who is product manager with Automotive with KUKA Roboter. And he'll be shining a spotlight on the latest industrial robots and cutting edge technologies and demonstrating how KUKA's energy efficient robot systems will reduce energy consumption, costs and emissions. Now, Peter joined KUKA Systems in 1990, overseeing the fieldbus communication and new line concepts for automotive body shops. In 1990, he moved to KUKA Roboter, where he was responsible for strategic product development for the automotive industry worldwide. Since 2012, he has been responsible for sustainability and energy efficiency inside KUKA. Now, before I pass over to him, I'd like to remind you all in attendance to draft up some questions which Peter will answer at the Q&A session following his presentation. Please ask your questions by typing them into the box in the lower right-hand side of your screen. If you should experience any technical issues during the session, please also type these into the Q&A box and our team will do the best to sort them out. We hope you find this webinar stimulating and informative. And I'll now hand over to Peter to begin his presentation.
Yeah, good morning. Thank you, Nick. So this webinar is about energy efficiency and sustainable production with industrial robots. And for the last 5 years, I think, automotive industry is thinking of the development of energy prices, because the slide that you see right here was a diagnosis of the development of energy prices for the next 30 years, and this was done before Fukushima and before the decision of many countries to drop their nuclear power plants. So I think energy prices will even rise more. But during the lifetime of a robot system, the energy prices will almost double in Europe from 10 euro cent to 20 euro cent. Natural resources become scarcer, and this will also affect energy prices. And now the saving energy by installing energy efficient robot system, at least this is what most of the German OEMs talk about, will be a new resource, a new source of energy. But right now, the development of energy prices is an incalculable risk. And so I think this means KUKA Robots, we will take care about this with energy efficient and sustainable robot systems. Now, what does this mean for us as a robot supplier? We have to define energy efficient robot systems. The first aspect is we have to reduce the weight of the robot arm with as small as possible moving mass. We have to reduce the power consumption of the robot during motion. And also, we have to reduce the power consumption during standby, because our customers will accept that the robot consumes energy if he is working, if he's productive. But they will not accept that the robot system will consume energy while just standing around and doing nothing. Online monitoring of energy consumption during production gives the customer, our customer, the possibility to define the energy consumption of the complete body shop or even the complete plant. We have to report as a robot system the energy consumption to an energy management system. The energy management system discussion started 2 years ago, and right now I think many of our customers will install an energy management system, and this means the robot has to supply the energy consumption data to this energy management system. We need strategies for energy efficient programming, and this means at least as a starter, we have to think about defining the energy consumption of a robot, not during production, but also in the phases of offline programming. So right now we are working on an RCS module that makes it possible to define the energy consumption of a robot during offline programming, so that the customer knows in advance how much energy the task of the robot will need. And of course, we have to think of recuperation of brake energy. So now we have two items in the beginning that I want to talk about. So I called it compact production with reduced moving mass. So now reduced moving mass means, of course, as a first step, a lightweight robot design. We have to make the robot arm lighter. And of course, we have to work on a reduction of heavy payload robots, because most of those robots with a payload of 360 to 500 kilograms weigh almost double than a standard robot with a payload of 300 kilograms. 4 years ago, we started the development of our Quantec series. And in this slide, you see in gray the contour of the old robot, the Series 2000, and in orange, this is the new Quantec family. And you see that this robot is much smaller, lighter. We were able to decrease the volume of the robot by 25%. We used innovative structural lightweight design and intelligent material selection to reduce the weight of the robots. So the result was, compared to the Series 2000, the new Quantec series, as a weight reduction of 12%. And by this, together with the KRC4, the new robot controller from KUKA, we were able to reduce the energy consumption by 30% compared to the old system. And we could be 25% faster. So now this is a decision of our customers, either to speed up the robot by 25%, of course, with an increased energy consumption, or to have the same cycle time as they had in the past with a 30% reduced energy consumption. I will later talk about the energy flows in a body shop, and the results of those analysis was that we have to have a very compact building, a small building, and this means we have to increase the robot density inside a production line, and this also means a very small footprint, minimized interference contours of the robot. So what we reached was a significant reduction of the moving mass, and by this of the energy consumption, and the extremely compact design for operation in high robot density cells. We did an analysis of many body shops, and the result was, and I will show the result on this slide here. Now here you see the reach, that's the x-axis, and the y-axis is the payload. And this is the, I would say, the 95% robot portfolio that you need in a normal body shop. In the past, this portfolio was covered by 4 different families of robots. Now with the Quantec family, we have 26 robots inside this family with many common parts. We made it possible to cover this complete portfolio of a body shop with just one family. So we offer 15 standard robots with a payload from 90 to 300 kilograms and a reach of 2.50 m to 3,100 millimeters. In addition to this, we introduced 11 shelf-mounted robots to cover all the portfolio of a body shop. So now a complete body shop, or let's say 95% of the body shop, could be covered by a member of the Quantec family. And this is interesting when it comes to weight, because all the 26 robots, the Quantec, they weigh around 1,100 to 1,200 kilograms, compared to a heavy payload robot that's more than 2 tons in weight. Now the result, we did another analysis. We had several portfolios of our automotive customers, and we tried to figure how many heavy payload robots we needed for our customers. And the result, when we selected the Quantec family for a body shop, was, as I said, a payload range from 90 to 300 kilograms and a reach from 2,500 to 3,900 millimeters. We were able to cover the complete portfolio by 69.5% only with the Quantec robots, and only 3.5% we needed heavy payload robots with a payload of 360 to 500 kilograms. So by this, of course, heavy payload robots are more expensive than standard robots. We made it possible to have a significant reduction of investment costs because of the very high percentage, 96% of standard robots. We were able to significantly reduce the energy costs due to the lower mass to be moved. And of course, it's only one family that you need in the body shop. We have optimized spare part costs because all the 26 Quantec robots have common spare parts. Compared to our competitors, the Quantec family, as I said, only needs 3.5% of heavy payload robots for a body shop. Competitor 1 needs over 20% of heavy payload robots, and the body shop portfolio could be covered only by 80% using standard robots. And another competitor of KUKA will require 37.4% of heavy payload robots, and only 60% of the body shop portfolio could be covered by standard robots. Now this results in a significant reduction of investment costs, as I already said, but also when it comes to life cycle costs. On this slide I added the weight of the robot arm in a 800 robot body shop, and compared to our competitors, you see that the KUKA body shop, the weight of all the robots, of the 800 robots, is next to 900 tons. Competitor 1 needs 20% more weight, and competitor 2 almost 50% more weight of the robots. And this means that we have a significant reduction of mass to be moved if you use the Quantec family. And by this, a reduction of mass to be moved means less energy consumption for the robots, and by this we have a significant reduction of life cycle costs. Compared to our competitor, let's say this is the standard spot welding robot KR210 with a reach of 2,700 millimeters. And you see it here. What we did, we tested our one competitive robot with using an OEM benchmark program. And as you see, the speed of the KR210 Extra You see it here. Now this is the shortest cycle time. We started with the override. This means speed of the robot, 50%, 60%, 70, 80, 90, 100%. And on the y-axis, you see the energy consumption. Now the result of this was, at the same cycle time, a KRC4 controlled quantic robot needs 30% less energy than the competitor robot, and we are 8% faster, running with 100% override than the competitive robot. And even if the quantic robot is faster, we need 6% less energy than the competitor robot. So this means the standard spot welding system, KR210, reached 2,700 millimeters extra. Is the worldwide benchmark in regards to speed and energy consumption. So now this is our standard spot welding robot. When our customers select speed, we have the so-called KR210, also reached 2,700 prime. Now this robot was specially designed for high-speed application, and using this robot it's possible to be 27% faster than our competitors. If you run, and you see it here in this area, if you run the prime robot with the same cycle time as the competitor, we use exactly the same amount of energy, but the possibility to increase production speed is at an end at our competitor because he already runs 100% override. With using the KR210 prime, you have the possibility to have a productivity buffer. You can speed up the robot, you can speed up the throughput of the line without adding new robots, new line or new cells, only by speeding up the robots. And this means, and this was why we specially did this robot development, the high-speed spot welding system is a worldwide benchmark for flexible, and it's very important for a demand-driven production. Without adding additional robots to a line, it's possible to increase the throughput of the production line. Now, energy efficiency is, I think, an item that you have to think not only in production, but also in planning. And now I will talk about energy efficient robot systems. A consumption forecast in simulation that is it will be, I would say, realized middle of next year, and the result will be a consumption flexible production of cars. To find out how to define energy efficiency or energy efficiency functions in the robot arm and also in the controller, we did an analysis of energy flows in a car plant. And you see it right here in this part here. So this is the energy consumption of a complete car plant. The biggest consumer, of course, is the paint shop with almost 60% of the energy. We have the press shop with 8%. We have the final assembly with 11%. And we have the body shop with 22%. This means less than 1/4 of the energy is consumed by the body shop. And then we did, you see it in this part here, we did an analysis of the energy flows inside body shop. So the result was quite surprising, not only to us but also for the OEMs. The result was that more than 50% of the body shop energy runs into the building. We have 38%, 10%, and 3% are air conditioning, light, water cooling, and only 49% of the energy is consumed by robot system, process equipment, transportation system, and so on. So if you look at the 49%, the requirement of the customers was to have new and highly energy efficient robot systems. And because of the 51% of the energy that runs in the building, we have to think of shorter and more compact production lines with a significantly increased robot density. And by this, we could have smaller buildings and so reduce the energy consumption of the building. In the next step, we analyzed the energy consumption of the robot in production, and again we were quite surprised by the results because you see it in this pie chart up here. The robot in motion. Now this is a time chart. What we did, we analyzed a 3-shift production Monday to Friday with Saturday and Sunday off. So it's 1 week. And over the 1 week, the robot was only moving 19% of the time. 81% of the time, the robot was not moving, standing around, consuming energy without being productive. 10% of the time we had shorter breaks. It was between 2 and 20 seconds. We had 26% of longer breaks. It was 20 seconds to 10 minutes. And we have 10 minutes to 3 hours. And the 28% is the time of the weekend. So now, if the robot is moving only 19%, you see it up here, of the production time, the 19% consume 72% of the energy that runs into the robot system. So if we think about the 72% robot in motion, we have to talk about a significant reduction of the moving mass of the robot and also an improved motion technology, path planning, and so on. And if we look at the 28% robot is not moving, we have to think of an optimized cycle sequencing of the robot and a frequent use of the so-called standby modes that are provided by Profi Energy or by, let's say, if we go to the Ethernet IP area, it will be SIP Energy. Now what did we do? Now we had the analysis of the robot energetic states, and here you see again 19% robot in motion, 10% robot is stopped with active drives, and so on. Now the first step that we did with the KRC4 and Quantec, with the lightweight design of the Quantec family and with the new drive technology and new path planning system of the KRC4 and Quantec, we were able to reduce the energy consumption of the robot in motion by 30% compared to our old system. Very interesting was, we call it blended braking. The part where the robot is stopped with the drives still active, especially if you move a body from one cell to another cell. This takes between 10 to 12 seconds. We apply the brakes after 20 seconds, so this means the robot is waiting for the body coming into the cell 12 seconds with active drives and with a power consumption between 600 to 800 watts. If we apply the brakes, it's possible to drop down to an energy level of 220 watts. So this we realized we have you can program into your robot program If you are at the end of the cycle, apply brakes immediately so that you wait for the body coming or going out and the new body coming into the cell. You don't wait the 12 seconds with 800 watts. You wait with only 220 watts. Now, if the robot system is waiting for 20 seconds up to 10 minutes, we integrated the temperature-controlled fan that controls the rotation speed of the fan, and by this we were able to reduce the energy consumption by 15%. If we have longer brakes, we supply the possibility to move to so-called standby modes. The standby modes are initiated by the PLC using the standard Profi energy protocol. For shorter brakes, between 10 minutes and 3 hours, we use standby mode 2. This means we shut the drive bus off, and by this we drop down from 220 watts to 140 watts. That's a reduction of 30% in the energy consumption. For longer brakes, we implemented the so-called sleep mode, and this means we completely shut down the system. Only the connection to the network is held alive, and by this we are able to reduce the energy consumption from 220 to 35 watts, and this is 80%. Now the result of all those measures, again the example that I showed in the first slide, the robot system based on a 3-shift production with a production break over the weekend, our assumption was the energy consumption in motion of the robot was 3 kilowatts per hour, and we were able to guarantee 5 million brake cycles. 5 million brake cycles are very interesting because what we try in the future is to apply the brakes as often as possible, because it makes no sense for the robot to wait for an interlock signal of the PLC or for the body getting out of the cell or coming in with drives activated. We apply the brakes as often as possible, but for this we had to exceed the warranty for our brakes from, in the past, 1 million brake cycles to right now 5 million brake cycles. And the result was, using all the functionalities that I described in the slide before, we were able to reduce the energy consumption of one robot by 2,500 kilowatts per hour per robot per year. And when it comes to the discussion of global warming or the carbon dioxide footprint of a product, I think it will be more interesting in the future to talk about the emission of CO2, and using all the functions we were able to reduce the CO2 emission of a robot by 1.5 tons per year. If we talk about money, this means the energy cost of a robot could be decreased by almost 250 euros a year per robot. We started this development, I would say, 2 years ago, and when I did a presentation 2 years ago to automotive industry, we were only talking about the 250 euros because it was cost, it was life cycle cost. But now with the discussion of global warming, carbon dioxide footprint, I would say for the last half year, the 1.5 ton CO2 emission becomes of more interest than the money. Now this robot is running in production. But if you think about energy efficiency, if your line is already built and in production, we thought it's too late to think about energy consumption. To think about energy consumption during startup, you don't have time because you want to get your line running. So our next step was to develop features that make it possible to do a consumption forecast during planning, because we thought that energy efficiency must be taken into consideration as early as the planning phase. So what we think will be the future, or at least we will have this middle of next year, the expected energy consumption of the application must be forecasted on the basis of a robot path programmed offline, as you see it here. You have a robot simulation tool, and on this side you have the so-called RCS module. Now what we did in the past, we used the RCS module to define the cycle time of the application. But now it's not only cycle time that the customer will be interested in, it's also the energy consumption. So what we did, it will be possible to do an offline programming and then ask the simulation software what's the cycle time and what's the energy consumption. So right now the energy efficiency can be improved by this, by adapting the payload category of the robot, the tool parameters, and the velocity. So this means during offline programming, you can optimize the energy consumption by
I'm sorry about that. We appear to have lost Peter. We're going to try and resolve that situation as quickly as we can. Just to remind you that if you have any questions currently for Peter, please type those down in the question box in the bottom corner of your screen, and Peter will be happy to answer those at the Q&A session at the end of this. Obviously, Peter's highlighted some very interesting areas that KUKA are taking their robot systems. The direction, not just in terms of speed and efficiency, but also in terms of construction of the actual robots and the energy efficiency. So hopefully this will prompt some clear questions. So are you back with us, Peter?
Do you hear me?
Yeah, we hear you now, Peter. Sorry about that. We seem to have had a technical glitch there, but if you want to continue, that's great. Thank you.
Okay. So now what I was at the adaptation of velocity and acceleration. So now the result of robot simulation will not only be reachability, accessibility, and cycle time. In the future, it will be based on energy consumption forecast. You can define the energy consumption not only of a robot system, not only of a cell or a line. You will know the energy consumption of a complete body shop before you even build up the body shop. When it comes to, we call it energy management systems. Energy management systems or to use energy management system is a requirement, at least from Brussels in Europe and also in Germany from the German government. This means that our customers have to know the energy flows inside a body shop, and this means they have to get all the measurements of robot, of process controllers, of positioning systems, and so on. And we call this the transparent energy balance. Now, transparent energy balance means that all the components of a body shop report their actual energy consumption to an energy management system. And this management system allows a detailed analysis, and based on this analysis it can be done optimizations and potential savings. Now Profi Energy, which we support, provides so-called measurement devices, and this means the PLC can ask the robot, using a standard profile, Profi Energy, can ask the energy consumption, the actual energy consumption over the last 100 milliseconds. Can also ask, we have another measurement, can ask the energy consumption of the last cycle and also the energy consumption over the last hour. And this means that by this we have a targeted analysis of energy consumption and production sequences. For the customer, we have the advantage that he can break down the energy costs either by model or by batch. And this is very important for the future, because if you look at the CO2 footprint of a product, it will not be possible to run several models of cars over the same line and then just take the average of the energy consumption and calculate the average energy consumption for each model. In the future you will have to know for each model, big car, medium car, small car, you have to know for each model the individual energy consumption. And this is breakdown of energy cost by model, and this can only be provided by using Profi Energy management measurement system. So this means if we have an analysis of the energy flows using the measurement systems provided by Profi Energy, we can avoid peaks in the energy consumption. And by avoiding peaks, as you see in this part up here, we have, or the customer will have significant purchasing advantages due to billing rate system of the energy suppliers, because the peaks are what costs money. So you can avoid peaks by doing a modeling of the energy consumption of your production system. You can do a production-related load prognosis for planning security. And we have this provides the base for the future consumption flexible production. Now, the consumption flexible production is, let's say it's an idea that I had 1 year ago. If we take all the functionalities that we are or will be able to provide during the next 1 or 2 years, we will have a completely new system, or let's say a new concept, a new philosophy in production, and I call this a consumption flexible production. Now what does this mean? If we come to a automotive OEM, so now the automotive OEM is customer driven. So first we have the customer behavior. The customer behavior is driven by motivation, emotion, lifestyle, geography. So in many cases it can't be forecasted. Now the customer behavior results in incoming orders. So the customer orders a special model, several customers, so different models, different quantities, and also the delivery date is very important for the customer. On the other side, we have the energy supplier, because the OEMs have to build those cars. Energy supplier, so I only put the sustainable energy supplier in there, hydropower, solar power, wind power. The energy supplier communicates to the energy management of our customer The energy management of an OEM always looks at the availability of hydro, solar, wind power. It controls the costs, and it looks after the CO2 footprint. Of course, hydro, solar, wind power, they're very good regarding the CO2 footprint. But if they have to take nuclear power plants or coal, the CO2 footprint will be of interest in regards to type of the energy that you need. So now it comes to production scheduling. You have the incoming orders, you have to build the cars, you know how much energy you have. This means the incoming orders create an energy demand, and the energy management controls the energy supply. Now, if we could provide in the future an energy model of the complete production in a body shop, we could define an energy optimized production schedule. And the measurement devices I talked about on the last slide, they are the source for the energy model. Using those measurements, you know for each model which robot, which component uses how much energy, so that you can model the production schedule in regards to demand and energy supply. As an example, if you have two cars, a big one and a small one, a big one with let's say 6,000 spot welds, the small one with 4,000 spot welds, it takes more energy to build the big one. Now, if solar power is cheap, available, with a very good CO2 footprint between 10 o'clock and 10 o'clock in the morning and 2 o'clock in the afternoon, it would make sense to build the bigger car with the higher energy demand during this time and do the smaller car with the 4,000 welds at a time of day where energy is either costly or with a not that good CO2 footprint. So now the energy model defines the production schedule, and the production schedule now is transformed to the consumption flexible production. And I think in the future we will have, let's say, concepts like this where our customers think of not, I have to do 800 cars a day without looking at the energy supply and the CO2 footprint. Now this was, let's say, a little bit future. Hopefully we will have this in the next 5 to 8 years. This was my last slide. If you have any questions, feel free to ask me. Thank you very much for your attention.
Thank you very much for that, Peter. It was a very interesting presentation to show the direction that KUKA are taking with developing their robot systems. We have a few questions for you. First off, Peter, I think just to touch on the subject that you've mentioned, the thread that's run through the entire presentation is your OEM customers, the demands they're now making on KUKA. Speed over energy efficiency, which are they prioritising more? You mentioned there that it wasn't the cost of the energy so much as the carbon footprint, but what are they prioritising now?
So I think the OEMs are changing very slow. In the past it was always speed, speed, speed. And if you talk to the planning guys, it is speed right now. But slowly, I think it will change. It has changed a little bit, but I would say even now speed is of more interest than energy efficiency.
We have another question here, Peter. Question is regarding the impact of accelerations and vibrations on the payload with I'm assuming with the new lightweight type robots. Can you shed some light on that for us?
Yeah, so the design of the Quantec is extremely stiff. So there won't be any vibrations, and also we added model-based closed loop control so that we get rid of all vibrations. But now regarding acceleration, so acceleration is, let's say, we need the most energy to accelerate. If the robot has reached the speed and is driving with the same speed, so he won't use that much energy. So it's acceleration. And I think in the future we will have to concentrate more on different concepts, how to accelerate. And I think one of the requirements that we will have in the future is to move the robot not as fast as possible, to accelerate and then brake or slow the robot down as fast as we can. But we will have a more smooth movement with, I think, less acceleration than we have right now. Because acceleration is the biggest part in energy consumption.
Okay, we have a few more questions here for you, Peter. The question is from our friends at AIDA. You've discussed assembly and body shop applications, but is there any press shop applications here that you can explain or discuss?
Press shop application. So now we do the press chaining robots. So we move the part from one press to the other press. I think it will be very difficult to save energy because the press chaining robots are our fastest robots. So they run real fast because with some presses we have cycle times of 4 to 5 seconds. And within the 4 to 5 seconds the robot has to pick up a part from one press and move to the other press, put the part into the other press, and then get out as fast as possible before the press closes. So if it comes to energy consumption, the brake energy recuperation will be very, very important because we have to keep the speed on press robots. But as we accelerate very fast, we also slow down very fast, and this means we have the brake energy. Right now we have just one resistor, and what we do right now with the energy is we make heat, or we transform it into heat. This is not energy efficient. So we are looking for possibilities to use the brake energy, especially with press robots, or not only press robots, it's also with very fast pick and place applications where we accelerate and then we decelerate very fast. So it's not only for automotive OEMs but also for logistic systems where we have palletizing robots that run very fast with a high acceleration and a very fast deceleration. And I think in those applications we will have to talk, I think, 100% about recuperation of brake energy.
Thanks for that, Peter. I mean, are you talking about brake energy recuperation in a similar way that's been applied to vehicles on the road for the future? Is that something that's conceivable for robot systems?
Yeah. Yeah, I think it will be very important. So right now we tested to increase what's the English expression? The capacity of the intermediate circle. That's one possibility, or to feed the energy back to the system. So there are different different possibilities to work on it. But now all the components that you need for that are very expensive. And right now we have to calculate the decreased costs for energy consumption, but the increased costs in investment. So it's always a calculation that you have to do.
Okay, thank you, Peter. That's very interesting. We'll look out for that in the future and the developments in that side of things.
Yeah.
Quick question regarding you discussed the volume and the weight of the new Quantex generation of robots. Has the lightweighting of the robots had any impact on the service life or the maintenance schedules of the robots?
No. So now we had a big discussion when we started with the Quantex, which materials should we use? And so the older system, the Series 2000, we had the link arm and the arm done in aluminum. Now we have a new, I don't know the English expression, but now only the link arm is done in aluminum. No, it's not the link arm. The arm is done in aluminum. And I think also when it comes to the CO2 footprint of a product, it's not only the product car that we talk about, it's also the product robot. And so we will have, as a robot supplier, I think the same requirements as our OEMs, but not with their cars, but we will have it with our robots. And so we have to decide in the future which materials to use. Sustainable materials, and also we have to think of recycling the robots.
Thanks, Peter. We have one final question from our attendees regarding the concept of Profi Energy, the system for monitoring.
Yeah.
The question is, what has been the response from the OEMs to this offering?
So now, of course, we provide the possibility with Profi Energy, but what we lack, or what the OEMs lack right now, is a software that can deal with this huge amount of data and just to store the huge amount of data. Because if you see in a body shop you have 800 to 1,000 robots, this is only robots. You have process controllers, you have shuttle, you have other drives, and that's a huge amount of consumption data that is collected by a energy management system. So right now, as far as I know, there is no energy management system available right now that can deal with this big amount of data. And okay, maybe it can deal with the big amount of data, but to do, based on those data, to do a model or to do a consumption prognosis, or to make sure with a defined scheduling that we don't have spikes in consumption. So now the base functionality is there, but right now we lack the higher level energy management systems that can deal with those functions.
Okay,
but I think
But
I think in the next 2 or 3 years we will have, there's several companies that are working on software like this.
Well, that's bringing us to the end of our session here, Peter. We've got a couple of very technical questions actually regarding your presentation. So we're going to forward those to you afterwards so you can respond directly, one from Tata regarding payloads. But that's a really interesting presentation. Thank you very much for that. You know, giving us a real insight there into the future of robotics and the options that are becoming available. Thank you very much to all our attendees for joining us today. The webinar is going to be uploaded to our archive and is accessible in the future for yourself and any colleagues who have been unable to attend the presentation. And you can access this and all our previous webinars on the webinar tab at the AMS homepage. Thanks very much again to Peter Klueger from KUKA, and thanks again for joining us. We hope you join us again for our next webinar. Thank you.
Thank you very much. Bye.